It's time for another amazing chemistry video with Mr. Stapleton. Proudly sponsored by Homologous Series. Nice topic.
Hi guys, welcome to the first video for the organic chemistry topic. I'm going to break this topic up into 10 different videos. Some of them will be quite short, some of them a little bit longer, just because there's 10 subtopics within this. This first one will probably be the one that goes mostly the longest, because I'll just cover some of the basics of organic chemistry. As always though, in the PowerPoint you'll see throughout we've got the YouTube play symbol there, and that'll take you directly to some of the other videos which go into more depth than what I'm doing just in the PowerPoint here. So if you see those, make sure you go and have a look at them. As I'm going through the PowerPoint, I'll try and hover over them so you can see the link as well, and that might be helpful if you just pause the video and you can have a look at it if you want more explanation. So basically what I'm going to be doing here is just an introduction around what is organic chemistry, what are organic molecules, and what sort of the basic organic molecules are that we'll be looking at to begin with. So an organic molecule is usually made up of carbon, hydrogen, nitrogen and oxygen. We don't have any metal atoms in there. We can introduce metal atoms later on as we start getting to what's called organometallic chemistry, and that's quite useful when we start getting into like drug therapy. But when we're talking about basic organic molecules, we have just carbon, hydrogen, nitrogen and oxygen. Carbon and hydrogen is the backbone. So you'll sometimes hear organic molecules referred to as hydrocarbons, and they form the basis of your organic molecule, and then you put in some reactive sides which are called functional groups. Okay, sometimes they're not just a straight chain, we have side branches as well, and you can just see some different examples here. Here's some of your basic organic molecules, and then you get into more complex drug-related structures. Now please, I'm in no means endorsing drug use in any forms unless that drug is caffeine. In the farmers union, nice coffee, in which case it's fantastic. Otherwise, drugs like this equals bad. Okay, just in case you weren't aware. So, when you're naming organic molecules, there's a few things you need to be aware of. Right? One is around how we name based on the number of carbon atoms. Another one's around naming with the functional group. And so I've done a lot of videos around the naming of organic molecules. This one's a good introduction on the basics, which I suggest you maybe have a look at. It goes through these 5 dot points. I have then done separate videos around just naming and drawing some structures for them, which I'll show you later on. But if you want a basic overview of alcohols and their reactivity, you can go to this one. If you want to look at things like carboxylic acids, ketones, and that says ketones and ketones, that should be ketones and aldehydes, which will have the carbonyl functional group in there. You can have a look at that one. And this one is around esters. Okay, and it not only goes through naming and drawing them, but also the reactions of them. So I'm not going to go through naming organic molecules more than just to have this slide up there and say watch some of the videos. And if you can get the naming and drawing down pat, it makes this topic so much easier. So what I am going to have a look at is just melting and boiling points to begin with, and how these change with organic molecules. So when you're looking at melting points and boiling points, what you need to be looking at is firstly the type of secondary bonds that hold the molecules together, because remember we're dealing with organic molecules, so they're not three-dimensional structures, they're not ionic or metallic structures, they're just got covalent bonds there, and they're held together by secondary bonds. The strongest of them are hydrogen bonds, then you've got dipole-dipole bonds, and then lastly the weakest are dispersion bonds. Now because most organic molecules are non-polar, they're pretty much held together by dispersion bonds, so the weakest form. There's a couple of functional groups like the alcohol, carboxylic acid, amine, and we'll talk about them later on, where they actually hydrogen bonds, they're much stronger. But first of all, look at the type of bonds, okay, and then secondly look at the number of them. Okay, so what we try to do to compare and predict boiling point and melting point is look at things that have a similar molecular weight. So here's a good example I found of octane, C8H18, and 2,2,4-trimethylpentane, which is also called isooctane. You can see they've both got the same formula. Different structure though, so these are called structural isomers. Structural isomers have the same structure but different, same formula but different structure. And you can see the boiling point of these differs quite significantly. Now it's obviously nothing to do with the type of secondary bonds, because these are both non-polar molecules, so they're both held together by dispersion bonds. So it comes down to the number of secondary bonds present. The long chain here of octane allows for another octane molecule to stack nicely on top, and you get lots of dispersion bonds forming between the hydrogen atoms. 2,2,4-trimethylpentane, however, when you put another molecule on top of this, you got these bigger methyl groups here, These methyl groups prevent the chains from stacking as closely together as they could in octane, and so you get less secondary dispersion bonds forming and hence a lower boiling point. Alright, so the rule is as the carbon chain length increases, the melting point and boiling point also increases. That's because you're allowing for more sites for secondary dispersion bonds, and therefore you're getting a high melting point. There's a YouTube video here again where I go through this in a little bit more depth and show some more examples, in particular focus on like the hydrogen bonding as well and dipole-dipole bonding and how that impacts on the melting point and boiling point. The other thing we're going to just look at briefly is around solubility for organic molecules. Now, like we said, organic molecules are generally non-polar, so there's two types of solvents. There's polar solvents and there's non-polar solvents. So polar solvents have a direction of charge, non-polar solvents don't have a direction of charge. Because organic molecules don't have a direction of charge and they're non-polar, they won't interact with polar solvents. So you get these two layers. So you quite often see this maybe at petrol stations. You might go there after it's rained and you'll see like this rainbowy shimmer on top of the water. That's oil or petrol that's there. It doesn't dissolve in the water. It's also less dense, so it floats on top. And this is why oil spills are such a major issue in the ocean, because they don't dissolve into the water. They sit on top, which can cause quite a lot of issues for marine life. So in order to dissolve in a polar solvent, such as water, it must either have a functional group that can hydrogen bond to the water, such as hydroxyl carboxylic acid amine, and it must have a small non-polar section. The only exception to that is if you have what's called a protonated amine or a deprotonated carboxylic acid. And I'm going to go into those in a lot more depth in the later slides, so I'm not going to come into it too much more. But just keep in mind that if you've got those sorts of things, you can make the molecule solvent in soluble in a polar solvent. So the rule is, as the carbon chain length increases, the solubility in polar solvents decreases. I'm just going to put myself up here for the moment because that'll be out of the way for the next couple of rules. If we're talking about non-polar solvents, obviously they're quite soluble in non-polar solvents. Non-polar solvents are sometimes called organic solvents as well. And to dissolve an organic solvent, you need to have basically no polar groups or very small polar groups and a large non-polar section. These are the four most common non-polar solvents that are quite commonly used. So this is dimethyl sulfoxide. We've got two methyl groups here, which are non-polar and can dissolve other non-polar materials. So you can see in dimethyl 4-amide, we've got methyl groups here. We've got some hydrocarbon groups through here in tetrahydrofuran, and acetone has these two methyl groups. So what makes them good solvents is that one, they're small molecules, and two, they've got non-polar sections there, which can allow them to form dispersion bonds to other non-polar molecules and dissolve them. A homologous series is, the word homo means same, okay, so a homologous series is one where all members have the same general formula. So what you can see through here with the homologous series we have is that each time all we're doing is adding in an extra CH2 group. So you can see through here as we go through the alkanes, which are the most basic ones, we've increased just by a CH2 each time. Through here with the alkenes, you can see we're just adding a CH2 each time. Probably should have done that one, doesn't really matter. You can see CH2, 3 lots of CH2 there each time, even with the alcohols. CH2, CH2, so we've got 2 of them there, and 3 here as well. 2 lots of CH2, 3 lots there. Didn't do both of them there, sorry. So each time, all we're doing with a homologous series is increasing the carbon chain length, which means that each one, as we're going, has a higher boiling point because it's got more secondary bonds being formed. What's common amongst a homologous group is the functional group here. So you see all of these alkenes have a double bond in them. All the alcohols have an OH group here, and these are the reactive sites. The carboxylic acids here have a carboxylic acid group, and those are the things that react and give them the same chemical reactivity. They just increase it by a CH2 each time. Now those functional groups that I've mentioned are what's called a reactive site in a molecule. So each functional group has a distinct structure and way of being named, and I'll go through those on the next slide. But what you need to know, and this comes back to that basics of naming for organic chemistry, is how to name chains up to 8 carbon atoms long. So these are the what we call the prefixes we use. So when we're looking at the number of carbons and we want to name something, we look at how many it has, and we use this: methyl, ethyl, propyl, butyl, pentyl, hexyl, heptyl, and octyl. So I suggest you really learn these 8. These are what you need to know for Year 12 chemistry, and you use these in conjunction with the different functional groups I'll show you on the next slide. Now what I've put together on these next two slides is just some examples of some of the functional groups that you need to know in Year 12 chemistry. So alkanes and alkenes I'll look at, and alkynes I'll look at just towards the end of this video. There'll be separate ones on alcohols and carboxylic acids. I've got some examples of each of the different functional groups and the naming and the drawing of them. This video here in particular goes through just the different functional groups, what the particular parts are and how you name them, so I suggest you have a look at that. Like I said, the other part of this is these other ones: ketones, aldehydes, esters, amines and amides. We'll have a look at all of these in separate videos, and there'll be some videos around naming and drawing them as well, so I suggest you have a look at those. So what we're going to finish off with in this video is just a basic introduction to the alkanes, alkenes and alkynes, which are the basic building blocks of organic chemistry. So all alkanes have the general formula CnH2n plus 2. You can see them here: methane, ethane, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. As I said, you need to know up to 8 carbon atoms, so you need to know up to octane. Alright. They're all what we call saturated hydrocarbons. That means they contain the maximum amount of hydrogen possible. They have the same physical properties, which means they have a low melting point and boiling point. There's only weak dispersion bonds holding them together. As we've explained, the melting boiling point increases and carbon chain increases because we're introducing more secondary dispersion bonds which require more energy, and they're insoluble in water because they can't hydrogen bond, and they do float on top because they're less dense. Alkanes don't really do anything other than burn, so you would have been done probably combustion reactions before. Make sure you can do those. Alkenes and alkynes become a little bit more interesting because you've got double and triple bonds which you introduce. So the functional group for an alkene is a double bond, right, and an alkyne is a triple bond. So the impact that has is, if I just go to a basic molecule. So if you can see this, this is methane, which is the most basic alkane that you can have. And if you increase your carbon chain, you can go up to, this is propane. So you can see here, we've got 3 carbon atoms, a tetrahedral arrangement around each of them. And if you connect these together to make your longer hydrocarbon chains, you just get them sort of, connecting on and making long chains. All right, they just sort of zigzag along because they're all saturated. Tetrahedral arrangement around the carbon atoms in those. But when you get to an alkane, you can now see the difference between an alkane has a double bond between carbon atoms, and so what that now does is that changes the arrangement around the carbon from a tetrahedral, which is what you normally find here, to a trigonal planar. Okay, now a trigonal planar arrangement obviously causes the chains to have kinks, and that's important when we get to something like the triglycerides later on. If you then increase it again and go from a double bond to a triple bond, okay, a triple bond between your carbon atoms, now what you've got is a linear arrangement of your carbon atoms, and again that has another impact upon how your structure works. Now those double and triple bonds are also reactive sites, so you can add across your double or triple bond. Okay, so we can add add atoms in and break that double and triple bond and make new molecules. It also means that they're not saturated, so they don't contain the maximum amount of hydrogen, which means when they burn with incomplete combustion. Alright. However, apart from that, they have very similar physical properties. They're held together by dispersion bonds, so they have low boiling points. They're insoluble in water because they're completely non-polar. Alright, so that's been a bit of an introduction to organic chemistry. I suggest you have a look at some of the different videos around drawing and naming them. There's one up here for looking at alkenes, alkynes, and alkanes that you might want to have a look at as well. As always, if you've got any questions though, just ask. Thanks guys. This is real love.